Hi, my name is Monica Joja, and I work with Timothy O'Leary at the University of Cambridge. Today, I would like to talk about functional connectivity measures applied on calcium imaging data. A couple of years ago, I was doing my PhD in the control engineering community on Granger causality, and I became interested in its applications in neuroscience. On this picture, I illustrate what I got when I applied Granger causality to human EEG data. This approach to use a statistical concept to detect connectivity is widely used for low spatial resolution data. But the question of this talk is whether it should also be used on data with single cell resolution. When the signal primarily comes from individual cells, the dynamics are coming from the physiology of the cells. Now, the good thing is that we know a lot about these dynamics, and thus this might help us in detecting connectivities between signals better than in low spatial resolution data. Our focus in this talk is on calcium imaging data that we can visualize as a combination of a repeating pattern of elevation and decay, highlighted in the black line, and then a fluctuation around the black line. To tackle the problem of detecting cell connectivities from calcium imaging data, I generated synthetic data and tested a couple of well-established connectivity measures. As a first step, I simulated data that mimicked different statistics of the real data, such as peak magnitude, peak intervals, the shape of the calcium elevation, and the fluctuations. To introduce the connection between the mimic signals, I chose a model that combines a nonlinear and then a linear signal propagation. The nonlinear signal propagation is highlighted by red, and it puts a threshold on the input and produces a point process that triggers these elevations of the signal. Another element in the model is a Gaussian input noise that accounts for hidden input cells that might trigger the output as well. The linear signal propagation is highlighted by green, where a constant alpha parameter determines the level of linearity. So there are two aspects of this linear part of the model. First, on the technical level, it introduces correlation between the input and the output signals, which is often present in real data as well. And then in terms of interpretation, it may account for common input. I consider two very different methods to test how they capture connectivities between signals. So one of them is the well-known Granger causality, and the other one is a less well-known empirical dynamic modeling. If you want to test whether X causes Y with EDM, you estimate X based on times when Y produced repeating patterns. Let's look at how this estimation works by demonstrating how this magenta point, which is X at T8 plus 1, would be estimated. So we first look at what happened in Y right before T8 and look for that pattern in the past of Y, which gives us time instances, these TIs. Then we go back to X and make an estimate of X T8 plus 1 by averaging TI plus 1s with some weights that are determined by how similar the corresponding patterns in Y were to the original pattern. EDM detects coupling between signals more easily than the direction of the coupling. And for the direction, we need to look at how EDM changes when the processes are lagged. So the right direction has a typical shape, like this green line, and it performs best at a certain lag. And typically the other direction just decays from zero lag. This method is somewhat complicated and computationally expensive, but it allows for incredible flexibility in the dynamics of the signals and the coupling of the signal. Granger causality is a very general concept, but its most common use is with linear models, and that is what I used to. I used the multivariate Granger causality MATLAB toolbox that helped me build local vector autoregressive models, and then I calculated Granger causality from those models. This method is questionable because it is based on linear models, and we know that in this case those are incorrect, but nevertheless it often performs surprisingly well. The performance of the two methods was calculated by using bootstrapping. Distributions of EDM and Granger causality were first calculated from decoupled signals, and that gave us a threshold to decide on the coupling of the signals. Then I tested the direction of the coupling separately. For both the coupling and the direction of the coupling, I will now show the number of failed cases out of 800 cases. So on the left, you see the results for EDM, in the middle for Granger causality, and then on the right for the combination of the two. So on the right, we detected coupling whenever either EDM or Granger causality detected coupling. What we can see is that EDM was better at detecting coupling and was a bit weaker detecting the direction of the coupling. We can also see that, contrary to my expectations, Granger causality did not perform well as the linearity of the model increased. And my guess is that it's because the nonlinearity was very strong, and then the combination of the two didn't help. Granger causality could not handle it well. Then at last, what we also see is that when we put together the two methods, we can significantly improve the performance. The take-home message is that the dynamics coming from the physiology of the cell is more prevalent in low spatial resolution data, and that suggests that we might need to look for other functional connectivity measures than what we apply for high spatial resolution data. What I would like to do next is to design a method for functional connectivity specifically for calcium imaging data, and then to use that to find evidences for neuronal plasticity and how it relates to representational drift, which is a very interesting topic that some of my colleagues have been working on. Thank you all for listening. Big thank for the Neuromatch organizers for the opportunity, and also to my supervisor, Timothy O'Leary, and my colleagues in Cambridge for their contribution to this project.